Hi, now let's discuss about instruments in medical practice. I want to give you about like 3 examples of measurements of body temperature, blood pressure, and oxygen saturation in the blood. So measuring body temperature, it's easy. You can see nowadays a very easy way to measure body temperature. But why body temperature is important? Because it's oftentimes first indication of abnormal conditions, especially our normal body temperature is about 37 degrees. And if it's elevated, that could be a sign of underlying illness, especially infection. And also, so that elevated body temperature is called hyperthermia. Okay, so this can occur prolonged exercise or exposure to excessive heat. So thermometer made of glass you are familiar with. This is only an estimate representing core body temperature. So we have thermometer under the tongue or armpit, and that may not be always accurate. So sometimes in special case, we may need to measure core body temperature directly. Here's an example of a figure that you see catheter-based measurement of temperature. So thermistor wire is within this lumen of catheter for measuring blood temperature. And you can see like this can measure blood temperature directly. However, you see this is risky and this is expensive and also invasive measure. So it's not always happening, but there are times to have this. And ear thermometer is sensing infrared light radiation emitted from our tympanic membrane with a pyroelectrical crystal. What this pyroelectric means? So pyroelectricity, pyro means a thermal. So materials responds to heat by generating electric potential. So it's like piezoelectric, when piezo means pressure-induced electricity. Pyroelectricity is thermal-induced electricity. Next, I want to discuss about sphygmomanometer, which is for measuring blood pressure. Okay, so that's this part of, and this pump and this gauge. And there's another one, which is a stethoscope, which is directly measuring the sound by using this diaphragm sensor and your ear. So this combination of sphygmomanometer and a stethoscope is a traditional way of measuring our blood pressure. So usually using your arms and measuring the right artery. So why measure blood pressure? This is also very important for knowing health status of your cardiovascular system. So this diagram shows that the artery in our arm, and you see these are arteries, so there's like pulsation directly from our heart, and that pressure cuff giving this pressure, and you first elevate the pressure high enough that you squeeze the artery until it doesn't flow anymore, and then you release slowly. Then what happens is, as you remember, that this narrowing makes the flow faster, and that gives a high Reynolds number or make the flow turbulent. Turbulent is irregular and making an eddy, and that gives you a specific sound of shh, 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 depending on your pulse together. So with that sound, we can measure the sound with the sphygmomanometer. So when we measure our blood pressure, and we will find out chronic high blood pressure, which we call tension. And that's defined by systolic and diastolic pressure as higher than 140 and 90 millimeter Hg. And what this indicates is a risk of cardiovascular disease, such as a atherosclerosis in your vessels, and heart attack or stroke has higher risk. On the other hand, you could have very low blood pressure, which we call not hyper, but yes, hypotension. And when does hypotension can occur? And if there's a big trauma that you lose your blood volume, and rapid blood loss can give you hypotension and also hypothermia, which could be dangerous because if you lack of blood, you lack of oxygen delivery to organs, and you lead to shock. So this is very important to catch if one patient have hypotension. So what are the normal range for blood pressure, which is about systolic pressure as lower than 120 and diastolic pressure as lower than 80 mmHg. And nowadays, these traditional measurement can be replaced by more advancement of technology, which is using, remember, mechanical sensor, using the measuring the pressure by the stretch of the surface of this cuff. So that is this electronic ways, and there's a mechanical strain gauge inside which measures the pressure directly. And even you analyze this data well enough, you can even measure the pulse rate as well. So given the high blood pressure, I just want to mention a little bit of the definition of high blood pressure. And you can see normal, below 120 and below 80 for diastolic. There's a pre-hypertension in this range, and high blood pressure or hypertension is defined as higher than 140 and higher than 90. That's stage 1 hypertension. If you are stage 2, that's dangerous. That's higher than 160 and 100 for systolic and diastolic pressure. And why this become a problem? Because you see, there are many of risk with higher involved with high blood pressure, such as cerebrovascular accident, stroke can happen more, and hypertensive encephalopathy, and apathy means that this kind of pathology involved. So you can have confusion, headache, and conversion. And retina of the eye is also sensitive for the pressure. And if there's hypertension, then hypertensive retinopathy, which affects our retina. And blood, this can leave elevated sugar levels, and heart, MI or myocardial infarction, which is simply heart attack can happen. And hypertension makes your heart abnormal, heart muscle or cardiomyopathy, or it can lead to heart failure. And also your kidneys as well. Kidneys filter a lot of your blood a day, like almost like over 1,800 liters, and that kidney can suffer from hypertensive nephropathy that leads to chronic renal failure. So one noticeable thing is you see over age, there are data showing blood pressure of this keep increasing. So even if you have a lower blood pressure, you're okay, but you see over age, your blood pressure is always tend to go higher and higher. Okay, so that's why we have to pay attention to this. And so because of that, let's talk about measurement of blood pressure. And traditionally, this is called auscultatory method. And auscultation is meaning as a listening to sound within the body. So this is to remember with a pressure cuff, and you release the pressure that is shown as a gray over time. So you release, and this red is your arterial blood pressure. So when cuff pressure is higher, then it squeezes. So it squeezes completely the artery, so you don't listen any sound. But once it's in between, then the flow starts to move, and that pulse generating turbulence will causes a sound, which we call auscultation, listening to sound. And so you see, listen the sound, and that's called the carotid cuff sound. And until the cuff pressure is lower than the actual arterial pressure, then you don't hear a sound because you're not squeezing the artery anymore. The artery will smoothly flow. Until you have this squeezement, then there is a sound here. So by detecting this carotid cuff sound, with higher beginning, and then later you can read systolic pressure and diastolic pressure. So detection of carotid cough sound with pressure cuff and a stethoscope. Okay, so when this method is not feasible, so that's actually when a patient has a underlying lung problem and you need to check CO2 and oxygen of blood frequently, then this method may not be useful. On the other hand, there are like a more precise measurement called catheter-based blood pressure measurement, that you want to measure blood pressure within a blood vessel. So this is invasive, only used when within specific vessel measurement is necessary. For example, if someone's are suspected as having pulmonary hypertension, which is hypertension only inside a vessel in the lung, then pulmonary artery need to be measured for blood pressure. So through the heart, the catheter-based blood pressure can get into right ventricle, right atrium. It goes to pulmonary artery so that it can measure the pressure of pulmonary artery. So, so that extravascular pressure measurement, I want to give you an example, which happened to be, I was involved in making this fiber optic-based Febrile pressure sensor based on lensed fiber and polymeric diaphragm. So what that means is we created a optical fiber where the light goes in and there's a lensed fiber was made, and that fiber is reflected from a polymeric diaphragm, which is polymer so that it responds to pressure. That tiny displacement can be measured by optical interference, and which can be detected by this optical spectrum analyzer with a broadband light source. So, and to create this, and we need to have a create this lensed fiber, and with having this electric arc discharge to make it like lens, so that we create this and we actually publish this one and generate patents. So that's kind of an example of very fine extravascular pressure measurement system. You could potentially use it for inside the body. And another is the intravascular pressure transducers, which is a very tiny. You see this out of this coin, and tiny sensors can be directly put it inside the vessel and measure pressure. So this is the diagram showing pressure sensitive beam and compensation of control, and the actual electron microscope shows these fabricated devices. So now, the next I want to discuss about the oxygen concentration. So blood carrying the oxygen to various organs in our body. The main way of oxygen carriage is by hemoglobin. You remember at the first time at the molecular principles, hemoglobin is a kind of tertiary structure with 4 subunits. Each can hold 1 oxygen molecule. So normal oxygen saturations for human is about 97 to 99% in healthy individual. And what does this oxygen saturation mean? And here's a simple diagram of hemoglobin do not have normally oxygen that we call deoxyhemoglobin. Once it gets oxygen molecule, that's oxyhemoglobin. So if none, 0%. Half of this hemoglobin was saturated, then that's 50. And all the hemoglobin will hold oxygen 100%. It's that simple. So a device to measure this oxygen saturation in our body, or how much of the hemoglobin is carrying the oxygen, is called pulse oximeter, so oxygen meter measurement. So oxygen saturation is the total amount of saturated form of hemoglobin, or we call, yes, oxyhemoglobin, compared to non-saturated form, or deoxyhemoglobin. And this oxygen saturation is an indicator of effectiveness of a person's ventilation and gas exchange in the lungs. So let me give you a formula. So that's percentage of a saturation of oxygen is, oxyhemoglobin divided by total hemoglobin C concentration. And total hemoglobin is composed of oxy and deoxyhemoglobin and multiplied by 100 for making percent. So to measure this oxygen saturation in the blood, the proper blood oxygen CO2, which is crucial for maintaining our pH and normal function of our cells. So to measure, we use a trick based on biophotonics and the optical property of the blood. You remember that some blood, when you cut, you can see a darker color of blood, but if you happen to have a, let's say, a real arterial blood coming, that's a bright red. So the different color means something, and that using that difference in color, or the color means the absorption of the light in visible ranges are different. And using that, we could actually quantify the status of oxygen saturation. So that's showing up in this absorption spectrum. What it means is you see this x-axis as a wavelength or color of the light, and y-axis is the absorption. So you can see bloods are usually red because of this high absorption in the green and blue range. And interestingly, the oxy-deoxyhemoglobin has quite different absorption. And you can see oxyhemoglobin has much lower in this 600 to 700, which is red color absorption is low. What that means is red color, when hit this hemoglobin, it will reflect more. That's why in our eye, it looks bright red color. So that's oxyhemoglobin spectrum and deoxy. So in principle, there's only two unknowns concentration. So you could just use two colors of light sending through the tissue and detect, and you can recover the concentration of two variables. So that's the trick. Low oxygen level or hypoxemia. Semia means in the blood. Oxygen in the blood is a low hypoxemia. So low oxygen level, it can be caused by lung underlying disease, such as asthma and emphysema and severe pneumonia and pulmonary edema. All of these affect airway and lung parenchyma, which will affect our proper oxygen gas exchange. And oxygen content in the blood is described as a percentage of oxygen saturation by taking arterial blood sample. So that's a gold standard. And the pulse oximeter, I brought a nice diagram here. And how do we measure sending this two color of light, such as, let's say, 660 red LED light emitting diode or infrared 910 nanometer, and then you need a detector, which I just described as a photodiode. So you see here, red and infrared, two kinds of LEDs are sending the light through the finger, and inside the finger there's a blood vessel, and so it will absorb, and you have a photodetector. So that measurement of by pulse oximeter monitors not only this concentration, your signal will fluctuate because of the heartbeat. So you can even measure heart rate or pulse rate with LEDs and photodiodes. And we use light absorbance at two different wavelengths. Oxyhemoglobin and deoxyhemoglobin has different absorbance characteristics at these two wavelengths. So that's the trick, and we are using it, and now this is very cheap. So the origin of pulse oximetry signal is described here, and I will skip this, but I'll just give you an idea that the actual signal from photodiode, what you get is normal signal. You see this heartbeat is showing, and also the degree of this height will give you the oxygen saturation. But it also shows low perfusion, noisy artifact, a motion artifact. So it gives us an engineering challenge and problem to how to analyze this signal and turn it into a oxygen saturation percent. So now I want to summarize typical medical instruments and example. Temperature, I show oral digital thermometer, which uses a thermistor as a sensor, and that output will give a temperature within the range of 32 to 40 degrees. Blood pressure, a simple one now has a digital sphygmomanometer, and the sensors are stethoscope or strain gauge. And the output pressure is 0 to 400 millimeter Hg, and blood oxygen we use pulse oximeter, and that sensor was a photodiode, and that gives a percent oxygen saturation from 0 to 100%. And electrical sensors, which I haven't discussed much, but that's called biopotential, and there's cardiac, biopotential neural, retinal, and muscle. And that we call electrocardiography, electroencephalography, or EEG, and electroretinography, and electromyography. And you can see there are different kind of skin, scalp, contact lens, and needle electrodes. And that's measuring the range of a millimeter to several hundred millivolt, which is happening at a biopotential inside our body. So, in summary of bioinstrumentation, we describe the general components of bioinstruments as the measurement parameter, and we use sensor, and we process it to receiver to display as an output. And we have to understand different type of sensors and the mechanisms of principle which converts its detected signal into something useful for us, that is usually electrical signals. And we discuss thermal, mechanical, electrical, and optical sensors. And I also discuss about generalized Ohm's law, that all these different types of mechanical, translational, rotational, hydraulic, and electrical have some similarity of the principle, which is making the change is driven by driving effort, and that rate of change, the ratio is giving you an impedance and generalized impedance, and which we can consider as kind of resistance in an electrical circuit. And we learned the basic concepts of evaluation of tests for disease diagnosis. So when we are developing an instrument or test an assay for disease, we have to understand this concept very well as accuracy and precision. And for the instrument itself, sensitivity and specificity is very important for different kind of disease nature, and also for the patient point of view, like positive or negative value are predicting the disease based on disease prevalence. So all these are very important when we develop this and to commercialize for the physicians or the end users, patients can use. And we discuss working principles and choice of bioinstruments in medical practice. Thank you for your attention.